Hello there and welcome back. So now let's move to tutorial 13. So in this case is do it by yourself, okay? So I will just give you some instructions and then it's up to you to set up the case. So basically what we're going to do in this case is the Ahmed body. Okay, so here you have the domain layout. Okay, so you have the geometry also, you can download it, but you have the drawings for the geometry. You can redo it, you can do something smaller, bigger, it's up to you. Okay, you can redo your mesh. So we're giving you something as a starting point. If you want, you can use it, or feel free to use something else. So basically this is what we have: inlet, outlet, then we have the walls as the walls. That is we don't have boundary layer, and then important, we have a moving ground. Okay, so when you set up the boundary conditions, you should also set up here the ground that is moving, just to simulate that as if the car were moving, you know, in the motorway. So this is a classical validation case for the car industry. Okay, there is a lot of data, but we are not going to push into the validation. We're going to give you a lot of margin of error to get the results. Our goal is just to see if you are able to set up a case from scratch. Okay. So you are asked just to compute the drag coefficient. Okay, so here you have the case setup, the working conditions. Okay, so working fluid will be air, incompressible, isothermal. Use the default properties. Okay, the inlet velocity is 40 meters per second. Okay, and remember that you will need to set something similar on the ground. You can also try to run putting this one as a wall, and you will see that there is a slight difference. You can check that. Okay, you have here the reference area to compute the the drag coefficient. Okay, so when you set up reference values, put this one, the velocity and the working conditions of the fluid. You can use any turbulence model. We have addressed that. Okay, up to this point we have covered a lot of theory, so now it's up to you to choose one, to pick up one. It's up to you. Okay, or if you want, you can test all the turbulence model. Okay, it's up to you. And then when you have results, do some standard post-processing. Okay, so you will need to compute vertical structures, integral length scales, the rate of integral length scales to grid length scale, couplings with velocity contours, all lines, separation lines, string lines, and so on. Okay, so do some heavy post-processing. Then also when you try to assess the goodness of the mesh, also if you are going to do your own mesh, try to do different meshes and see how things change according to the mesh. By the way, the mesh that we're given is a wall modeling mesh. You can go ahead and use a wall resolving mesh. Also try to do some sampling, okay, at any location in the water surface or in the domain, just to plot normalized velocity, but also in the domain you can do this. And you can run in a steady or in a steady, okay? But remember that you need to compute your statistic. So talking about the validation, so we're not focusing to pinpointing the precise value. We are just interested in seeing if you can set up the case and get something within an acceptable margin. So this is the drag coefficient, and here we're giving you a lot of margin of error, okay? So you have a minimum and maximum. So if your final value comes within this range, I think it's acceptable what you are doing. Okay. Again, it will depend a lot in the mesh quality. Okay. So if you get a super fine mesh, it's likely that you will get something that will be closer to the numerical result, to the experimental result. If you are using wall functions, maybe you will be a little bit farther. You can assess all that. Okay. As I say, there is plenty of validation data for this case. You have the link in the web page. You can download it. We put some references there. Okay, and we're just interested in the CD, but there are also in the web page, you have a links to another web page where you can download some experimental data. You have some velocity profiles on the Ahmed body. Okay, so it's up to you if you want to do a more detailed validation case. So here you have the references. Okay, so feel free just to visit those. And what I was mentioning about this is an interesting one. Okay, so just let me go here and show you. Okay, so as you go here, you will have a lot of experimental data. See that in different locations of the body. Okay, so you need to read well where in reference to what is that is specified. But here you have different velocity profiles. Okay, so you can try to validate that. Okay, and also there are some numerical some numerical solutions, and here you have some additional references there. Okay, so this is an interesting link. So you have the references there. Okay. And before showing you some colors now, what I'm expecting from you, so remember that we address a lot of things in different turbulence models, but also we talk about a little bit some models have deficiencies. Now, so this is a question that always people ask. So how do I choose those options? Now, how do I enable options? And just by looking at the geometry and having a minimum insight about the physics what you're trying to do, you can get an idea of what model will be the better and what corrections you need to enable. So these are the questions that you should ask yourself. So are there large stagnation points? Okay, look at the geometry and try to answer this question. Then, are there sharp angles that can generate concentrated vortices? Remember that we looked at this at the curvature correction. So this will be related to the production limiter, curvature correction, or even the choice of the turbulence model of the solve with the vortex generator case. Is there a strong system rotation, swirling effects that you might need to resolve? That meaning that you will need to use a more sophisticated model, okay, to take into account the anisotropic behavior or nature of the flow. Okay, are there regions that cannot set periodic vortex shedding? And remember, we go back to one of the first tutorials, the unsteady one, the cylinder, that we have the unsteadiness, the von Karman vortex strip behind the cylinder. So are there regions here that might generate that? Because this is immediately an indication that you need to use an unsteady solver. Okay, do expect large flow separation. So by looking at the geometry, you can also get an idea. Okay, is there surface roughness? Now we talk about the surface. And finally, is the steady hypothesis acceptable for you? Okay, so just try to answer these questions and you will get an idea how to choose your turbulence models, corrections, and set up your case. And just to show you some figures here, so see that here we have already have the results. So answering the previous questions, are there large stagnation regions? Look at here, the domain, the Ahmed body, and yes, there are large stagnation regions. So it might be desirable to enable that correction, that production limiter. Okay, if you are using linear viscosity models. Are there concentrated vortices? Look at here. Yes, there are two big concentrated vortices here, but as you look down the body, you will see that there you have the stills, the support of the body, that those those geometries, those solids can also generate something similar to the von Karman vortex strip. So things that you need to analyze, but yes, you have some concentrated vortices. Then we look at velocity controls and what I was mentioning previously. Okay, so here this is a coupling, and here in the bottom where you have the support of the body, and see that you have these small cylinders, and this, as you see here, you have a wake. Is this wake strongly unsteady? I don't know, it's up to you to assess that, or maybe you can neglect this because you will realize, okay, this is a small portion of the geometry, so it won't affect strongly my whole drag or lift computation. See here also that in the rear part of the body you have this separation. It might be strongly unsteady, or it might be something that is, let's say, midly unsteady. Okay, so maybe the hypothesis for steadiness is a good one here. Okay, you will need to assess that. Then we look at integral length scale. Remember that we talked about this during the first lectures, but also when we address post-processing. Okay, that you can compute this using two equation models. By the way, using these models, you can compute these quantities, and this is just telling you where you have the largest vortices, and it's a very good indication to know where do you need to have finer meshes. Okay, so you know that you have the whole wake, and basically this is telling you that, okay, this region you have largest vortices, so maybe it will be desirable to refine the mesh there. By the way, I'm filtering this one, so I'm not putting the whole color. So using a filter, I'm just showing the quantities that are above a value. Okay, so then remember that also we talk about the grid refinement ratio that is related to the integral length scale, but also with the mesh, and we mentioned that it's desirable to have this grid refinement ratio more than 5 if you want to resolve the unsteadiness. Okay, is you go to scale resolving the simulations. This is very desirable. If you stay into the steady hypothesis, it's not necessarily, but it can be advisable just to go a little bit larger to resolve better the vortices. Well, see here that this one is basically telling you where you need to add more cells to resolve better the vortices. So see that if we talk about that the bottlenecks to be larger than 5, see that here kind of we're about 3. So basically kind of we need to double the mesh all around the wake. Okay, so see that this one is just showing you where you have the integral scales, where you need to put more cells. Okay, and now if I draw the mesh, okay, I have the cut planes and I'm not filtering now. So see that you have this mesh, and basically clearly you can see here, for instance, here when you have the transition chance between these small and large cells, okay, you see that the refinement ratio drops fast. Okay, so probably would be a good idea to extend the whole refinement box all the way to the outlet, and also you can refine a little bit more this refinement box here just to get closer to 5, okay, as you see here. But it's telling you precisely where you need to do that. Okay, it's not that you need to do it in the whole domain, so maybe you will need to add some other boxes, refinement boxes, to be more selective and to avoid increasing the cells too much, the cell count too much. Again, remember that in Fluent that you have that very nice tool for adaptive mesh refinement, so you can try that tool. However, I will always recommend to refine the mesh not using your meshing tool, because when you use that adaptive mesh refinement, it will add hanging nodes. Okay, and this guy, I'm not a supporter of hanging nodes, but they work. Okay, but be careful when using those hanging nodes. So those were just the general instructions, and just going back to the, you go to the website here, see that you will have here, okay, the instructions, you have the drawing, okay, so you can take this drawing and do your own geometry and do also different domain, and giving you just one domain, okay. So here you have the mesh. Okay, so you are going to, I'm giving you a mesh here, a clean mesh. I'm not giving you the case, you need to do the whole setup. And here you have the geometry, also only the space clean geometry. Also you have the edges, so you can modify that using space cleans or the same modeler or on shape, whatever you use. Okay, so you have all the files here to start from scratch. Okay, so remember, this case is for you from scratch, but I already gave you a lot of information. And finally, if you want some validation data here, you just download the paper. So you have a few papers there, mainly a collection that I have from here and some other master theses. Okay, so this is a very interesting case. Okay, so we're doing this in sense very simple, just drag coefficient, but see that many things can be measured. Okay, so that's all for this case. Okay, I hope you managed to get it running. Okay, so if you manage to get this case working, I think you are in a very good track. Okay, you understand everything, and at this point you will realize that what you need is just computational resources, because we have the knowledge. Okay, that's all for the moment. Thank you very much for your attention, and see you in the next final tutorials. Bye.